Good day. For those of you who do not know me, my name is Douglas Harder, and this topic we're going to discuss using eigenvalues and eigenfunctions to solve homogeneous linear ordinary differential equations with initial conditions. So in this topic, we will discuss how the differential operator is indeed a linear operator. We will see that the differential operator does indeed have eigenvalues and eigenfunctions. We will see that these eigenfunctions are then used to find solutions to a system of ordinary differential equations. We will see that this results in unknowns, and these unknowns can be fixed based on initial conditions. And again, let's remind ourselves that this is entirely supplemental information. This will be covered in detail in second year. However, in this case, we are simply using this as a demonstration of how eigenvalues and in this case, vectors, can be used to solve analytic problems. So this is important. So enjoy this, observe what's happening, and recall that in the real world, you won't have to explicitly calculate the eigenvalues and eigenvectors, but rather you will just use a computer to get those details. You will then use those details to analyze your system. Now recall that for a vector u to be an eigenvector of a matrix A, we must have that A applied to u, or A times u, is a scalar multiple of the vector u. Recall also that the defining property of a linear operator is simply that that operator applied to a linear combination of vectors is that same linear combination of the operator applied to each of the vectors individually. For differentiable functions, is the differential operator linear? That is the derivative a linear operation? Well, you know from calculus that the derivative of alpha times t x of t plus beta times y of t is indeed alpha times the derivative applied to x of t plus beta times the derivative applied to y of t. So the derivative of a linear combination of functions is that same linear combination of the derivative applied to each of the functions. So yes, the differential operator is indeed linear. So referring back to the definition of an eigenvector, we may wonder, does the differential operator actually also have eigenvectors? That is, are there any functions that you're aware of where the derivative of that function is a scalar multiple of that function? Actually, you should recognize this. The derivative of e to the lambda t is lambda times e to the lambda t. So yes, indeed, here we have the derivative being applied to a function being a scalar multiple of that function. And the interesting thing is it doesn't matter what value of lambda we have. It could be 3, it could be -1, it could be -75,221.3289. The derivative of this exponential function is lambda times this same exponential. Consequently, every real or even complex number is an eigenvalue of the differential operator, and the corresponding eigenfunction is e to that eigenvalue times t. Now, can any polynomial p of t be an eigenfunction of the differential operator? That is it possible for a polynomial, when differentiated, to end up being a scalar multiple of that polynomial? Well, not really, because if the polynomial is of degree n and n is greater than 0, then the degree of the derivative must be n minus 1. So there's no possibility that, for example, the derivative of a quadratic is a scalar multiple of a quadratic, for the derivative of a quadratic must be a linear polynomial. Therefore, no non-constant polynomial can be an eigenfunction. However, how about the constant polynomials? Well, wait a second. Yes, that actually does work. The derivative of a constant is equal to 0. That is, the derivative of a constant is 0 times that constant function. Thus, the constant functions are actually the null space of the differential operator. But notice also that the constant functions are actually exactly those functions e to the 0 times t. So this is actually just a special case of a trivial exponential function. The trivial exponential function when it is e to the 0 times t. So remember, the derivative applied to constant functions produces the zero functions, and for functions, the zero function is the zero vector for functions. Now, engineering deals with forces in the real world, and forces are described by derivatives and second derivatives. So, in some cases, you may have two or more systems or forces where the response of one system depends on the response of other systems. So, for example, in an electric circuit, you may have capacitors, inductors, and resistors. This would form a linear circuit. The response of the inductors will be changing depending on the charge on any of the connected capacitors that are storing charge. Alternatively, you may have a nanosurface, and you may have different points of pressure on that surface, and that pressure may be causing that surface to deform. You may like to determine what is the deformation that will take place. This, of course, requires you to solve such systems of ordinary differential equations. You're going to learn a lot more about this in your second year calculus courses. So for this topic, just watch and enjoy. So, in such cases, we may end up with a system of homogeneous linear differential equations. You'll notice that we have the derivatives of x, y, and t are linear combinations of the functions x, y, and t, and these coefficients describe how these solutions are coupled or how they affect each other. Now, notice that we can rewrite these ordinary differential equations using vector notation. So, a vector of the derivatives is simply equal to that matrix times that vector of those functions. So again, the first entry, the derivative of x of t with respect to t, is just equal to a11 times x of t plus a12 times y of t plus a13 times z of t. So consequently, we have a matrix. Now, we would like to find three functions, x, y, and z, each of them being functions of t, such that all three ordinary differential equations are satisfied. Well, without proof, we're going to find that we can do this as follows. Given this particular matrix A, all we want to do is find the eigenvalues and corresponding eigenvectors of that matrix. It can be shown, and you will see that this is true in second year, that the solution to this differential equation or system of differential equations is simply an unknown constant times C1 times the first eigenvector, and it doesn't have to be normalized, times e to the first eigenvalue times t. This is added onto a second constant that is unknown times the second eigenvector times e to the second eigenvalue times t, plus a third unknown times the third eigenvalue times e to the third eigenvalue times t. And of course, you can see that this generalizes to n ordinary differential equations in n unknown functions. All right, so this is something we can give to a computer. If we have modeled our system, then we can simply plug all of these matrices into a computer and out pop the eigenvalues and the eigenvectors. However, we have, in this case, three unknowns. Where do those show up? Well, the three unknowns, in this case C1, C2, and C3, are free variables that are going to be fixed by initial conditions. Basically, what is the initial state of the system? So, for example, what are the charges on the capacitors? What are the currents passing through the inductors? Or what are the initial stresses on your nano surface? Now, these initial conditions tell us the state of the system at time t equals 0. Generally, engineers prefer time t equals 0 as that is the time that we assume that the system is being turned on. For example, we may know the initial charge on the capacitor. It may indeed be 0. There may be a fixed current passing through an inductor. Or, again, there may be forces or tensions on a nano surface. So, in this case, at time t equals 0, then we need to know what values of C1, C2, and C3 give us these initial conditions. Well, we know that what the initial values are, x0, y0, and z0. And you'll notice that e to the 0 is 1. Therefore, we simply have that a linear combination of the eigenvectors must equal this initial condition. But wait a second, that too is a system of linear equations. Therefore, we can solve that. That gives us the unknowns C1, C2, and C3, and consequently, we can find the exact solution. So we will do this. We will look at two examples, one with a system of two ordinary differential equations with two initial conditions, and then we'll do it again with a system of four ordinary differential equations and four initial conditions. And in each case, we will find a unique solution that satisfies the differential equations and the initial conditions. All right, let's start with this system of two differential equations. You'll notice that they are coupled. The derivative of x depends both on x and y, and the derivative of y depends both on x and y. All right, the right-hand side of this system of two ordinary differential equations defines a matrix, specifically the matrix -2, 2, 1, -3. You will notice, therefore, that the vector of the derivatives of the two functions is equal to that matrix A times the vector of the functions x of t and y of t. So A times that vector is -2 times x of t plus 2y of t. And the second entry is x of t minus 3 times y of t. So now the vector is not just a vector of values, but rather a vector of functions. Now this matrix A has two eigenvalues and corresponding eigenvectors. They are not orthogonal. After all, the matrix is not symmetric. And we do not need normalized eigenvectors. However, with these eigenvector and eigenvalue pairs, with these eigenvalue-eigenvector pairs, we can claim the solution is as follows. Some unknown constant C1 times the first eigenvector times E to the first eigenvalue times t. So the first eigenvalue was -4, the first eigenvector was -1, 1. All of this is added to C2 times the second eigenvector 2, 1 times e to the second eigenvalue times t. The second eigenvalue was -1, so e to the negative t. Now, this is a vector-valued expression. You can also just write it as x of t is -c1 times e to the -4 times t plus 2 times c2 e to the negative t. And y of t is c1 times e to the -4 of t plus c2 e to the negative t. So suppose that we know at time t equals 0, both of these functions have these two initial values. So x at time t equals 0 is a function that has a value of 7, y at time t equals 0 has a value of 8. So you could also write it down as two separate equations. So in this case, we have that e to the -4 times 0 is just 1, and e to the -0 is also equal to 1. So therefore, x at 0 is this linear combination of the unknowns c1 and c2, and that must equal 7. Y at 0 must be c1 plus c2, and that must equal 8. Well, here it is written as a vector-valued expression. So we have c1 times the first eigenvector plus c2 times the second eigenvector is equal to the vector 7, 8. Of course, this defines a system of two linear equations in two unknowns. So there's our augmented matrix. It's equivalent to this matrix, and therefore the unknowns must be 3 and 5 respectively. All right, so given this solution, we can now substitute these two values into the two solutions. This gives us the following two functions. We have two functions in t. That's it. There's no more x of t or y of t on the right-hand side. Just that both x of t and y of t are linear combinations of exponential functions. You'll notice that these functions satisfy all of these conditions. If you were to take the derivative of the first function, x of t, then you'd see that the derivative does indeed equal -2 times x of t plus twice y of t. Similarly, the derivative of y of t, you can do that calculation yourself. You can calculate the derivative of y of t. That would be -12 times e to the -4t minus 5e to the negative t. And you would see that that is equal to x of t minus 3 times y of t. You'll also notice that x of t evaluated at time t equals 0 is indeed 7. -3 plus 10 is 7. And y of t at times t equals 0 is equal to 8. 3 plus 5 is equal to 8. Incidentally, here are the two functions when plotted. You will notice that as time goes to infinity, both of these functions go to 0. This is an ideal case for an engineering situation. Essentially, we should return to the steady state, or the solution, x of t equals y of t equals 0. All right, let's go a little bit crazy. Here we have a system of 4 ordinary differential equations. W, x, y, and z are all functions of t, and they are related as described by these 4 differential equations. So essentially, the derivative of w of t must be equal to twice x of t plus y of t minus twice z of t. All right, let's carry on forward. As before, this system is described by the following matrix A. And for brevity, I will use the dot notation, where a dot over a function name indicates a time derivative. So therefore, a vector of the time derivatives is equal to that matrix A times those functions. So for example, the time derivative with respect to w is equal to 0 times w plus 2 times x plus y minus 2 times z. Matrix vector multiplication. Thus, this matrix A has these 4 eigenvalues together with their corresponding linearly independent eigenvectors. You'll notice that the eigenvalue -1 is repeated, but there are nevertheless 2 linearly independent eigenvectors for this particular eigenvalue. Now, you don't have to find these. You would never be required on the examination to, for example, find the eigenvalues and eigenvectors of this 4x4 matrix, at least not in an exam. And in the real world, you would simply use software to find these eigenvalues and eigenvectors, and then you would use them appropriately. You'll notice also in this particular case, these eigenvectors are not normalized. But if they were, not an issue. We would just carry on with the normalized vectors and we'd still end up with the exact same solution in the end. Consequently, with these eigenvalue-eigenvector pairs, we can substitute them into our equation. The solutions are some unknown C1 times the first eigenvector times e to that first eigenvalue times t. The first eigenvalue is 6, plus C2 times the second eigenvector times e to the negative t, as the second eigenvalue was -1, and so on and so forth. And you can, of course, expand this out to get the following 4 equations. Again, we still have 4 unknowns, C1 through C4. Again, we're going to determine these based on initial conditions. Suppose that at time t equals 0, we have the following initial conditions. So w at 0 is -7.5. For example, if w was recording the charge on a capacitor, then that may represent -7.5 coulombs. X at 0 may be 8.5. That may be the current passing through an inductor. And so on and so forth. Y at 0 is -0.5 and Z at 0 is 20.5. Substituting the initial time t equals 0 into the equation, we get therefore that this linear combination of vectors must equal these initial conditions. Again, that looks exactly like a system of 4 linear equations in 4 unknowns. So here's the augmented matrix, and from what we saw previously, we can solve this to get that C1 through C4 are these 4 values. Now, substituting these into our general solution gives us what we see here. Again, if you prefer, you can just write it as 4 different functions, and noting that 2 of the eigenvalues are equal, we can combine them into this simpler representation. Now, with this solution, you will note that these functions satisfy all of these conditions. For example, if you were to differentiate w, which would be -18 times e to the 6t plus 10 e to the negative t minus 16.5 e to the negative 3t, you would find that this does indeed equal twice the function x plus y minus twice the function z. Additionally, you'll note that the first function, for example, when evaluated at 0, does indeed equal -3 minus 10, which is -13, plus 5.5, which is -7.5. And the same is true for the balance of the functions. Consequently, we have found a solution to this system of 4 ordinary differential equations together with these 4 initial conditions. By the way, here are those solutions plotted. Now you'll notice that these solutions diverge to infinity. This is likely not an ideal engineering situation. It would be preferable if such a system did not, say, for example, have the capacity on a capacitor go to infinity. After all, at some point, the capacitor would therefore overload, and this would likely result in a short circuit. So this may not be an ideal solution to an engineering problem. Following this topic, you now understand that eigenvalues and eigenvectors can be used to find solutions to systems of homogeneous linear initial value problems. You know that you're not required to understand the details for this course, but you are aware of how differential equations, when they are linear, can be translated into a matrix. Given that matrix, you can then use the eigenvalues and eigenvectors explicitly to find. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!